Good day everyone, I am Princess Seda Ramos presenting the study published in MDPI Remote Sensing, the automatic early warning to derive eruption source parameters of paroxysmal activity at Mount Etna, Italy. So this research advances the real-time volcanic hazard response through a multi-sensor early warning system. Mount Etna, a highly active European volcano, frequently experiences hazardous paroxysmal eruption. So timely detection is paramount. So this study introduces a near real-time automatic early warning system. So it leverages the multi-sensor data to identify the eruption transitions and estimate crucial eruption source parameters vital for the hazard modeling and aviation safety. So this study aimed to automatically detect the transitions from the strombolian to paroxysmal activity in real time. Second is to estimate the top plume height and the mass eruption rate for hazard assessment. And the third is to enhance the eruption response times by providing the timely data to aviation and the civil protection agencies. So this study focused on Mount Etna, Sicily. So the data set comprised 36 paroxysmal eruption from 2011 to 2021. So they utilizes the multi-sensor data, the thermal imagery, infrasound data, and the Meteo Sicilia weather radar, providing a robust validation platform. So this figure displays a digital elevation model of Mount Etna, highlighting the four summit craters, the southeast, Boca Nueva, Warjine, and Northeast. So this strategically positioned infrasound arrays, the ETN 250 meters aperture and the MVT is 150 meters aperture. So these are shown in the part C and D, detailing the transducer placements. And the E integrates all the sensor location, ensuring the comprehensive spatial coverage of the eruption signals. So this early warning system integrates three sensor types. First is the infrasonic system, second is the thermal camera, and the third is the weather radar. So each system provides a unique and complementary information for eruption detection and the characterization. So this figure, the infrasonic system early warning flowchart. So the core variable is the infrasound parameter, a dimensionless value derived in real time from infrasound array signal energy. So the system autonomously classifies activity into three alert levels. The EW0 yellow for the background activity. EW1 is orange, indicating the escalation towards paroxysm. And the EW2 red for the sustained high energy explosive activity. So this IP-based approach enables automatic alert triggering without manual waveform analysis. So continuously evaluating energy levels for real-time decision. So this system is particularly sensitive to the initial explosive phases of an eruption. For the thermal camera's early warning mechanism, the key variable here is VEX, the exit velocity of pyroclastic material in meter per second, infer from the upward movement speed of hot material in thermal images. So similar to the IS threshold defined alert levels, the EW0 yellow for background, EW1 is orange for the rapid velocity increase suggesting imminent transition, and the EW2 red for sustained high velocity ejections characteristic of the lava fountains. So the thermal cameras are crucial for monitoring, especially under poor visibility conditions. So the rapid detection of increasing exit velocities provides timely indication of the escalating eruptive intensity. So for the weather radar's role in estimating the eruption source parameter, the critical variable is the QM, the mass eruption rate in kilogram per second, directly relevant to assessing the eruption's impact, particularly for the aviation safety. So the radar detects plumes and calculates QM based on the radar reflectivity. So the alert thresholds are the low QM for the color orange for minor explosive phases, and the high QM is red for intense paroxysmal activity. So upon detecting a plume of sufficient height and the concentration, the radar transitions to 3D tracking mode to analyze the plume dynamics. So the radar provides crucial quantitative data on plume characteristic once an eruption has developed. So this figure presents the visual confirmation of eruptive activity through thermal RGB imagery from the ENT camera across various eruption dates. So each panel captures high temperature eject. The uncalibrated temperature scale ranges approximately from the negative 20 degrees Celsius to 80 degrees Celsius, with warmer areas appearing red and cooler areas blue. So these timestamp images are vital for correlating physical activity with sensor readings and visually validating the eruptive intensity across different events. So these images provide a direct visual link to the data captured by the other sensors, aiding in interpretation. So this figure 6 and 7 display the synchronized time series for the April 2011 and the April 2012 paroxysms. So each graph tracks the QM, the blue, the IP is red, and the VEX is the magenta. So vertical dashed lines indicates the EW1 and the EW2 trigger time. So these figures demonstrate the power of the multi-sensor approach. Notice that the IS or the IP and the TC system detect changes earlier, triggering the EW1 before the WR shows significant increases. So the system successfully captured the escalation pattern of both events. So in validating its robustness is providing early indication of paroxysmal activity. So the lead time provided by infrasound and thermal data is clearly evident here. So this figure 8 through 11 continue the detailed monitoring with multiple December 2015 paroxysmal events again, tracking the QM, IP, and the VEX. So observe the consistent trend across these events. A clear increase in IP and VEX precedes the peak in QM. So this reinforces the capability of the infrasonic and the thermal signals to act as early predictors of explosive activity, offering the crucial lead time for warning. So the consistency across the multiple events strengthens the reliability of the early warning indicators. So for this figure 12 and 13 illustrate the most recent eruption from February 2021. So on the February 16, both IP and the VEX showed the early spikes, triggering the EW1 and the EW2 significantly before the WR recorded high QM value. So a similar pattern occurred on the February 23rd, with IS and TC acting as an initial detector. So this time lag, often up to 1 to 2 hours between the initial acoustic or the thermal detection and radar confirmation, is strategically vital for enabling timely emergency responses. So this significant lead time underscores the potential of the integrated system for the proactive hazard mitigation. So this next figure present the integrated paroxysmal early warning system workflow. So the system initiates when the first EW alert is triggered by either the infrasonic system or the thermal camera. So this EW1 triggers the weather radar to enter the exploring mode. So if the radar subsequently detects a volcanic plume, the event is upgraded to EW2 and the radar switches to monitoring mode, activating the 3D plume tracking. So this coordinated approach, where the system cross-verifies signals, minimizes the false positives, and enhances the overall reliability. So this integrated workflow maximizes the strengths of each sensors while mitigating the individual limitations. So this model has potential applicability to other volcanoes with similar sensor deployments. So for these tables, provide a quantitative performance analysis. So for the table 1, details the precise time each system triggered the E1 and the EW2. So it's offered the clear chronological view of the system responses across the different events. So the table 2 quantifies the lead time, comparing the early response of one sensor relative to another. So the key metrics include the infrasound radar lead time, often ranges to 30 to 120 minutes, and the thermal radar lead time, which showed moderate success. So the success rates highlight that the IS system achieved 88.9% accuracy in detecting the strombolian pace, while the TC system had the 55.6% success rate for the lava fountain detection. So these tables provide a crucial metrics for evaluating the system performance and the relative contribution of each sensor. So the data clearly indicates the significant value of infrasound for early eruption detection. So in summary, the integrated early warning system utilizing the infrasound, the thermal cameras, and the weather radar significantly enhances the detection and response to paroxysmal eruption at Mount Etna. So the infrasound system can provide the alerts up to 2 hours before the plume formation is confirmed by radar. So the radar then provides crucial quantification of the plume parameter. So this multi-sensor approach reduces the false alarm and improves the safety for the aviation and the civil agencies. So the success at Mount Etna suggests the potential applicability to other volcanoes with similar sensor configuration warranting the further validation. And that concludes my presentation. Thank you for listening.